Welcome. This is a time series analysis course. My name is Nigarta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. This lecture is on a case study for modeling heteroscedasticity. And in this lesson, I will continue the analysis of the exchange rates with a focus on the prediction. For this example, we predict the currency for the last 2 months of the time period, the months of July and August 2017. The predictions are one lag ahead, obtained on a rolling basis. That is, we loop through all the time points to be predicted. We set the past data as being the time series observed up to the time point at which a prediction will be made. Then, fit the Arma-Garch model with the specifications provided for the two models in the previous lesson, but this time the model is fitted on the time series observed up to the time point at which a prediction will be made. Thus, with each prediction, the training data set changes. After the model fit, the one lag prediction for both the mean and the variance are obtained using the U-Garch forecast R function. We thus obtain predictions at each time point within the time period of the 2 months. We apply the same code for both models and for all three currencies. The prediction accuracy measures for the forecast of the mean for the different Euro-USD currency time series are on this slide. The measures are computed for both models. The first model being the ARMA with order 6.3 and Garch with order 2.1, and the second model being ARMA 0.0 and Garch 2.1. The prediction accuracy is lower for the second model across all measures, indicating that the model where the conditional mean does not depend on time performs better than the more complex model for the conditional mean. As pointed out in previous lectures, generally the precision measure is most appropriate in comparing prediction accuracy within this type of modeling. The smaller this measure is, the more accurate the prediction is. The measure is approximately 1.04, indicating that the proportion between the variability in the prediction versus the variability in the new data is 1.04. Thus, the variability in prediction is similar to that in the data. These are the prediction accuracy measures for the mean prediction for the Brazilian real USD dollar currency exchange. Similar results are noted as for the Euro USD currency, although the prediction accuracy is slightly worse for the Brazilian real currency than for Euro. These are the prediction accuracy measures for the mean prediction for the Chinese yuan USD currency exchange. Again, similar results are noted, but the prediction accuracy is slightly worse than for the other two currencies. This is the R code for comparing the mean predictions to the observed time series by overlaying the predicted means for the two models to the observed time series. Here are the plots. The predicted means are close to 0, with some variations in the predictions performed with the more complex Arma-Garch model for the Brazilian real and Chinese yuan currencies. Note that the mean predictions do not capture the variations in the different time series, since these variations are due to the variance, not to the mean of the process. Last, we'll take a closer look at the predictions for the volatility. The comparison now is between the squared time series data and the predictions of the conditional variance or volatility. The plots for the three currencies are here. The volatility is not well captured by the forecasted conditional variance for the euro currency, but it is captured much better for the other two currencies, particularly much better for the Chinese yuan. To conclude, we have seen that a joint Arma-Garch model performs differently across different time series. Note also that the volatility for the euro currency was smallest among the three currencies, while the predicted volatility captures much better the conditional variance in those time series with higher volatility. The Garch model introduced in this lecture provides the basis for the development of many other extensions of heteroscedasticity models. In the last lesson in this lecture introducing gauge models, I pointed out several other extensions such as exponential gauge or integrated gauge. These extensions and others provided on this slide are meant to deal with different distributions of the volatility, for example, unsymmetrical response to positive and negative shocks, large or small vortices, meaning more or less heavy tail distributions, among others, or nonlinear relationships with the past conditional variance. The good news is that many of the models are already implemented in the R statistical software, and most of them can be applied through the UGauge spec and UGauge fit functions from the RUGauge library used to fit the joint ARMA gauge models. In order to specify the other model types, you'll need to specify the model into model options of UGauge spec. The default is the gauge model. Let's compare these models using the difference currency exchange rate time series for the Euro USD, US dollar. Because we have learned from the joint modeling of the conditional mean and conditional variance that the conditional mean does not vary with time, I focus here on the modeling of the conditional variance. The code for forecasting the conditional variance is not different from the one provided in the previous lesson and thus not provided here. This is the plot of the predicted variance along with the observed squared time series shown in black. We see that the other models for heteroscedasticity have not improved the estimation of the volatility since none of the predictions capture the ups and downs in the squared difference time series. It's possible that such variations are due to randomness alone rather than serial correlation. I'll note here that running the forecasting code with all the 5 models and for a large number of time points at which we obtain predictions took more than a day of computational time. Such models are computationally expensive, and his real-time predictions are not possible even using more efficient computations. This is one drawback in the implementation of heteroscedasticity models in general. This lesson concludes the analysis of the exchange rates for US dollar versus 3 currencies. And I concluded this lesson with a comparison of the predictions. Thank you.